This video is going to show you how to use the Fick principle to solve for cardiac output. As a quick review, in previous videos I've shown that the volume of oxygen consumed, VO2, is equal to cardiac output, which represents the delivery of oxygen via the blood, times the AVO2 difference, which represents how much oxygen was used by the muscle. This video is going to show how you can rearrange this equation to solve for cardiac output. So if you're given, or if you figure out someone's VO2 max, and you assume an average AVO2 difference, what that person's cardiac output is likely to be. So let's start with an example. We have Terrence, who is 75 kilos and has a VO2 max of 50 mils per kilogram per minute. If we assume he has an average AVO2 difference of 150 mils of oxygen per liter of blood, what is his maximum cardiac output? Remember, AVO2 difference can be expressed one of two ways, the way I've got it here, as well as you might have seen it as 15 mils of oxygen per 100 mLs of blood, 100 mLs of blood. So the first thing we're going to have to do is we're going to have to convert Terrence's relative VO2 max in mils per kilogram per minute to an absolute VO2 max in liters per minute. The second thing we're going to do is we're going to rearrange the Fick equation to solve for Q, so we have to isolate Q. And the third thing we're going to do is solve for Q. So let's start off with number one. In a previous video, I've shown you how to convert a relative VO2 value to an absolute VO2 value. So we would go here for mils of oxygen per kilogram per minute. But you might recall, normally I express absolute in liters per minute, but today we're going to express it in mils of oxygen per minute. The reason being is that AVO2 difference in the question I gave you is given in 150 mils of oxygen per liter of blood. So to simplify, so I don't have to do too many conversions, I want to make sure I express my VO2 in mils of oxygen. So therefore, I'm converting my relative value to an absolute, but the absolute will be expressed in mils of oxygen. This will become clear later on. So to start, I'm just going to enter my values here. So Terrence has a VO2 max of 50 mils of oxygen per kilogram per minute. And I know I want to convert to just mils per minute. So I need to get rid of, so to speak, his body mass. So if it's on the denominator here, I have to put it on the numerator in my conversion factor. So Terrence is 75 kilos, and obviously 1 goes below, but you don't have to put the 1 in there. Kilograms will cancel out, and I'll be left with just units of mils of oxygen per minute, which is what I want. So I need to multiply the numbers on top, 50 by 75, and I don't worry about the ones, because anything multiplied or divided by 1 is the same number. And I end up with 3,750 mils of oxygen per minute. And that's Terrence's absolute VO2 expressed in mils of oxygen. The next thing I'm going to do is I'm going to rearrange the Fick equation to solve for Q, and this is from high school algebra math. So obviously I want to isolate Q here. So to isolate Q, what I'm going to do is I'm going to divide both sides by the AVO2 difference. So the right side I'm going to divide by AVO2 difference, and recall a number divided by itself. So say for instance 2 divided by 2 is going to be equal to 1. So we're using that principle here. And I'm obviously going to divide the left side by the same number or AVO2 difference. Obviously here, the AVO2 difference cancel out, and I'm going to be left with cardiac output being equal to VO2 divided by AVO2 difference. And I'm just going to rearrange this so I have cardiac output on the same thing. So it's the same way, just reversing the order there. Finally, we're going to solve for cardiac output. So Q max is going to be equal to VO2 max divided by AVO2 max. And if I put my numbers in here, remember we had a VO2 max of 3,750 mLs of oxygen per minute, and we're going to divide that by 150 mLs of oxygen per liter of blood. By looking at this, you may think, oh, the units are messed up. But I'm going to show you how, if you take 3,750 divided by 150 at this point, you'll get the right answer. I'm just going to show you where the units do cancel out. So expressing this fraction this way, so unit over unit over unit over unit, is going to be the same as, so if I take 3,750 mLs of oxygen per minute, and I multiply by the reciprocal of the AVO2 difference. What I mean by reciprocal is I take the denominator, liters of blood, and put it on the numerator. And I take the numerator, 150 mLs of oxygen, and put it on the denominator. So if I multiply by the reciprocal, it's the same as divided by that number. Here I show you that we can cancel out our mLs of oxygen, and notice now you see the reason why I left the absolute VO2 in mLs of oxygen instead of liters of oxygen. If I left it in liters of oxygen here, they wouldn't have canceled out. So I can take 3,750 and divide by 150, and I'm left with a cardiac output of 25 liters of blood per minute. We're going to continue on with this example. We've shown how to figure out Terence's maximal cardiac output, assuming he has an AVO2 difference of 150 mLs of oxygen per liter of blood and a VO2 max of 50 mLs per kilogram per minute. We figured out in the first part of this that his Qmax is 25 liters of blood per minute. If I was to say Terence is 25 years old, what is his theoretical maximal stroke volume? And again, stroke volume is how much blood is ejected from the heart with each beat. So if you recall, cardiac output is equal to stroke volume times heart rate. So we're going to use this equation now to solve for stroke volume. So the first thing we need to do is obviously rearrange this equation to isolate stroke volume, and then we're going to solve for it. So let's start off by rearranging this equation. Again, I want to isolate stroke volume. So to do this, I'm going to divide both sides by heart rate. Heart rate obviously cancels out because, again, any number divided by itself is 1. And I'm left with stroke volume being equal to cardiac output divided by heart rate. Again, I can just express it like this. So now I'm going to solve for stroke volume. I'm going to enter my cardiac output, which is 25 liters of blood per minute. And assuming Terence is 25 years old, I'm going to take 220 minus his age, which is our simple, easy, predictive maximal heart rate, and get a maximal heart rate of about 195 beats per minute. Again, I'm just going to show you how I've made sure my units will cancel out, but if I take 25 liters per minute cardiac output divided by 195 beats per minute, I'll get the correct answer here. But just to show you how the units cancel out, if I take 25 liters of blood and multiply by the reciprocal of 195 beats per minute, so that being minutes from the denominator goes in the numerator, beats goes on the denominator, I show you that our units of minutes cancel out, and I'm left with 0.128 liters of blood per beat. At this point, you might be looking at this, if you know your numbers for stroke volume, and going, I've never heard of stroke volume being equal to 0.128. The key here is that we need to convert stroke volume to mils per beat. That's how we usually express stroke volume, mils per beat. So if you were a little concerned that you actually had the wrong number, you don't. You need to make sure that you express things in the way they're usually expressed. So again, quick conversion. I want to convert liters of blood to mils of blood. So liters on the numerator here, goes on the denominator, and we're converting to mils. We know there's 1,000 milliliters in 1 liter. Just to check, liters gets to cancel out. And if I take 0.128 times 1,000, I'm left with a maximal stroke volume of 128 mils of blood per beat, which looks a lot more sensible for a maximal stroke volume.